Section 5.4 is on the normal distribution, and in this section we're going to look at normal distributions, and we're first going to consider a little investigation here. And there was a couple of mistakes in our original notes book here, so I just made a few changes, and I've already entered this data into a calculator and done the one variable statistics on the graphing calculator and gotten the following information: that the mean for this set of data is 19.8, the median is 19.8, and the mode is 19.8, and the standard deviation is approximately 3.03. So what you notice from this set of data is that the mean, median, mode are all the same. And when we did a frequency table, when I did a frequency table to generate a histogram, I used an interval width that was equal to the standard deviation of 3, and because the lowest data value in the table was 13.7 and the highest data value was 27.3, I started with my interval starting off at 12 and went up in an interval width of 3, so 12 to 15, 15 to 18, so on. And then when I tallied up the data values in my frequency table, I got the following results. 12 to 15, there were 3 pieces of data in that interval. 15 to 18, there were 8. 18 to 21 were 16. 21 to 24, 9 pieces of data. 24 to 27, 3 pieces of data, and 27 to 30 was 1 piece of data. So when I construct the histogram, and there's not enough room there to put titles, but the vertical side should be labeled as frequency. I guess I can write it here. And the horizontal axis would be the data values, which are representing hours. And the title, I guess, for the graph could be hours playing video games. So if we look at the, so I just labeled it hours playing video games in 1 week. So if we look at the histogram, the data, it kind of has a symmetrical type pattern, and that's what generally happens when you have a large set of data. If it's a representative of the population, and most times it will have what we call a normal distribution or a symmetrical pattern, where the mean, median, and mode are the same, and then you get so many within so many standard deviations of the mean. You expect a certain percentage of data to be within so many standard deviations of the mean, and it has this kind of a, if we were to construct a frequency polygon from this, I'll just use a different color here, from the midpoints of each of these bars, we would see that it's kind of got a, this one will go down to 0 there, it's kind of got this bell-shaped pattern. So what do you notice about the shape of the graph? The shape of the graph is symmetrical. And it says draw a frequency polygon, explain its shape. Well, we already did that, and it was a bell-shaped pattern. Kind of went up and then came back down. Now we were using straight lines to connect it, so it looked more, in our case, triangular, but it really should be called a bell-shaped pattern. So if we look at the description down here below, it says in many situations, if a controlled experiment is repeated and the data is collected to create a histogram, the histogram becomes more and more bell-shaped as the number of data in the distribution increases. Such repeated measurements will produce bell-shaped distributions which exhibit the characteristics of a normal curve. And so the picture that's here is basically the kind of a shape you'd be expecting. Data is symmetrical about the mean, so the mean lies in the middle of the data, and it's also the median. So this is if you have a normal distribution. As the mean is located where the curve is at its highest point, it's also the mode. And the mean, median, and mode are all equal in normal distribution patterns. Alright, so if we kind of examine your normal distribution patterns and look at within so many standard deviations of the mean, you can see that if you're looking at this bell-shaped pattern, if you're approximating the percentage of data that's to the right and left of the mean, it looks like it's exactly half the data, so about 50% to the left and to the right. So 50% to the right, 50% to the left of the mean. And if you had to look at within one standard deviation, so you can see these kind of lines here, one standard deviation, if you had to give an approximation of that, to me, like there's probably a little bit more than a half, so if we said approximately 70% of the data, because there's still these pieces on the end. And if you look at within 2 standard deviations of the mean, this shaded area would represent that. That's almost all the data, but not quite, so maybe 95% might be a good approximation. And then within 3 standard deviations of the mean, it almost looks like it's the entire data, so close to 100%. Might be a good approximation. So if you look at the diagram below, it kind of, for whatever reason, darkened when we put it onto this iPad, but the normally distributed data, if you look, the percentages there are listed for you. Within 1 standard deviation of the mean, you've got the 234%, so that would be 68% of the data, so our estimate of 90% was pretty, 70% we said was pretty good estimate. Within 2 standard deviations would be this 34, and the two 13.5s. So if you add all of those up, that adds up to 95% of the data, which I think was what we said. And the last one within 3 standard deviations of the mean is 99.7% of the data. If you add up all these percentages, the 2.35, the 13.5, and the 34 on both sides, you would end up with 99.7% of the data lie within 3 standard deviations of the mean. And that's close to 100%, obviously, so our estimates were pretty good. So using that idea that if you know that data is normally distributed, you can get an idea of how much data falls within so many standard deviations of the mean and answer questions related to that. So we'll try a few. Okay, our first example is Jim raises Siberian Husky sled dogs at his kennel. He knows from the data that he's collected over the years that the weights of adult male dogs are normally distributed with a mean of 52.5 and a standard deviation of 2.4. So to sketch a normal curve to represent this data, you would put the mean at the middle here. And then you would use your standard deviation of 2.4 to label each of the other lines there on the normal curve. So 52 plus 2.4 would be 54.9. Would be the label for the first standard deviation to the right. And then if you add another 2.4 to that, you get a 57.3. And then if you add another 2.4 to that, you get 59.7. And then to go on the left side of the mean, you just basically subtract the standard deviation. So 52.5 subtract 2.4 is 50.1. And then subtract another 2.4, we have 47.7. And then you subtract another 2.4, you get 45.3. And I can't really fit them in here because of the way the black went, but you should put the percentages in there. And within 1 standard deviation on either side, you should have 34%. You won't see, I don't know if I try it in red. I put 34% and 34% here. and then you'd have 13.5 here, and 13.5% here, and then you have 2.35. Percent, and then 0.15 on the end here, and the same thing on this side. 2.35 would be right here. It's very difficult to write small with this pen. And then 0.15% for a total of 100%. So the next question says, what percent of adult male dogs at Jim's Kennel would you expect to have a weight between 47.7 and 54.9? So if you look, 47.7 and 54.9 are basically is basically between these two lines here. So that would mean that your answer would be 13.5% plus 34% plus another 34%. So if you just total those up on your calculator, you would get 34 plus 34 plus 13.5, 81.5%. You would expect 81.5% of the male dogs, adult male dogs, to have a weight between 47.7 and 54.9 pounds. Another question, the assessed value of housing in Bay Roberts is normally distributed. There are 1,200 houses with a mean assessed value of 180,000. Standard deviation is 10,000. So to sketch a normal curve for that, you would have the mean would be 180,000 here in the middle. And then you add on your standard deviations to go to the right, so that would be 190,000. And then 200,000. And then this one here would be, 210,000. And going this way, of course, you'd be taking off 10, so this would be 170,000 and 160,000 and 150,000. So what percentage of houses have an assessed value between 170,000 and 200,000? So that would be from here up to here. And I forgot to label my percentages. This would be 34% here, 13.5% here, 2.35 here, and 0.15 here. And the other side would be 34 first, and then 13.5. And then 2.35, and then 0.15. So if you add up the percentages between the lines marked 170 and 200,000, you would have again 34% plus 34% plus 13.5%, which is again 81.5%. That's not always the answer, but it just happens to be in these two examples. How many of the 1,200 houses will have an assessed value between 170 and 200,000? So we just found out in B that 81.5% of that, so 81.5% of the 1,200 houses should have that percentage, that have that assessed value, and 0.815 times 1,200 then would be 978 houses have an assessed value. between 170,000 and $200,000. Question number 3. The number of centimeters of snowfall for the month of December for the last 5 decades is recorded on a normal distribution curve shown below. The values on the horizontal axis differ by 1 standard deviation. So the first question asks you what is the mean of the data. So that'd be 15 centimeters. Standard deviation, and that would be the difference between your mean and one line there, or on this side as well, same thing. If you take the difference there, 18, take away 15, will be 1 standard deviation, or 3 centimeters would be the standard deviation. What are the values for A, B, C, and D? So if you're looking for C, you just basically add a standard deviation, so that would be 18 plus 3. So C should be equal to 18 plus 3, which is equal to 21 centimeters. And then D would equal the 21 plus another 3 centimeters, which is 24 centimeters. And to get B, you would just have to take the 12 and take off a standard deviation of 3 centimeters, so that would be 9 centimeters. And A would be one more standard deviation back from B, so it'll be 9 take away 3 equals 6 centimeters. D, what percentage of the snowfalls recorded were between 12 and 18? So if you look at our normal distribution, we know that within the first standard deviation there should be 34% to the left and right of the mean, which means there should be 68%. Should be between 12 and 18. Between 9 and 21, and we know that this B was 9 and C was 21, so that would mean we would have to add on the 13.5% that's here and the 13.5% that's here. So that would be, if you add those up, you'd get 95%, because that would be 13.5 and 13.5 is 27, and 27 plus the 68 is going to be 95%. And less than 6 centimeters, well, this would be 6 was the label for A, so less than 6 would be the percentage that's in here, which would be 0.15%, because this would be 2.35, and this would be 2.35 as well on this side. And this would be 0.15 here. So less than 6 would be this part right here, which is 0.15% of the snowfalls. Question number 4 shows the scores on a standardized test normally distributed for 2 classes. What do these graphs have in common? They're both normally distributed data. Distributed data, and they both have the same mean. And if they're normally distributed data, then they should have the same. If they have the same mean, they should have the same median and mode as well. Okay, mean of 52. How are they different? Class A is a little bit more clustered than Class B. Class B is more spread out. Which means it has a larger standard deviation. Oh, I just answered the question for C, which has the greatest standard deviation, and that would be class B, since the data is more spread out. If a student scored 42 on a test, which class is he more likely in? And 42 falls, if we look, use the red here, 42 would probably be around here somewhere. So if we look at the likelihood that he's in a certain class, you look at class A, that would be in like probably the less than 13.5% or less, probably around 2.35% of students scored less than 42, around there. So that seems to be in a smaller percentage. So more than likely, he would probably be in class A. I'm sorry, class B. That was class A. Was the so more likely to be in class B, because 42 on the B graph, there's more students who scored, like the 13.5% would probably be down, or 2.5, I'm sorry, 2.35 would probably be down here somewhere. So this, the 42 is in the more majority of the data than class A's would be, falls within a range that's a majority. Question number 5. A business found that the lengths of 5,500 of their special candy canes for the holidays are normally distributed in centimeters, as shown below. What is the mean of the data? And the mean would be your middle piece here, which is 20 centimeters. Standard deviation would be the difference between your mean and that first line there, which is 0.5. There's a difference of 20.5 minus 20, or 0.5 centimeters. What percentage of candy canes have a length between 19.5 and 21 centimeters? Well, that would be one standard deviation of the mean there, so that would be basically 34%. And that didn't come out too great. So it would be 34% here and 34% here. So it'd be 68%. What percentage of candy canes are longer than 21.5? So if we continue labeling our normal curve, this would be 21, because you add on a 0.5, and then you add on another 0.5, it would be 21.5, would be here. So longer than 21.5 would be this portion right here, which is 1, 2, 3 standard deviations above the past 3 standard deviations from the mean. So this would be, if you remember our percentages, this would be 13.5, and this would be 2.35%. So this would only represent 0.15%. And how many of the candy canes have a length between 19.5 and 21? Well, we use from question C, we have 68% of the 5,500 candy canes, which is decimal 68 times 5,500. So 3,740 you would expect to have a length between 19.5 and 21 centimeters. And the next question, how many of the candy canes are longer than 21.5? Again, if we go back to the earlier question D, that would be 0.15% of the 5,500, which would be 0.15 times 5,500, which equals 825. Candy canes would have a length longer than 21.5 centimeters. Question F, why is it not possible at this time to determine the percentage of candy canes that are longer than 20.68 centimeters? And that's because 20.68 is not one of the 20.68 is not one of the labels on our normal distribution curve. Okay. Curve. So therefore, you can only use the percentages based on one of the labels that are there on your normal distribution curve, and 20.68 is not one of those labels. Okay, the next question. 2 baseball teams were traveling to Canadian summer games. The members of each team had carry-on luggage for their sports equipment. The masses of the carry-on luggage were normally distributed with the characteristics shown below. I think that M is a mistake there, I'm not sure. Okay, so this little symbol here means mean, and this symbol here is standard deviation. So for the men, there was a mean of 6.35 kilograms with a standard deviation of 1.04, and for the women there was a mean of 6.35 kilograms with a standard deviation of 0.59. So it's a sketchograph to show the distribution of luggage for each team. So not a whole lot of room there, but we'll try to fit it in. So we would have for the men, sorry about the graph, it's pretty sad looking. So you'd have 6.35, and then standard deviation of 1.04, so that would be, the next one would be 6.35 plus 1.04, or 7.39, and the next one would be plus 1.04 again, 8.43, and the third one would be plus 1.04, 9.47, and below this, the mean would be 6.35, subtract 1.04, 5.31, and then subtract from that another 1.04, and you get 4.27, and subtract another 1.04 from that, and you get 3.23. And I can't really fit the percentages in there, but you should put them in there. 34%, 34%, 13.5%, 2.35 would be there, and 0.15 here. And the same thing on this side, 13.5, 2.35, and then percent symbols, and then 0.15. And for the women, you would have a mean of 6.35, but this time you'll be adding 0.59. So that'd be 6.94 plus another 0.59, 7.53, plus another 0.59, 8.12, and then on the left it would be 6.35 minus 0.59, which is 5.76, minus 0.59 is 5.17, and minus 0.59 is 4.58. So again, you would have 34%, 34%, 13.5%, 2.35%, and 0.15%, and 13.5 on this side, and then 2.35 on this, and then 0.15 on the last. Okay, Part B says the women's team won the championship and each member received a medal and souvenir baseball with a combined mass of 1.18 kilograms, which they packed in their carry-on luggage. And sketch a graph that shows how the distribution of the masses of their carry-on luggage changed for the flight home. So basically we'd still have a normal distribution pattern, and if every single person's luggage went up by 1.18, was it? 1.18 kilograms, that would mean the mean would go up by 1.18. So the new mean now would be 6.35 plus the 1.18, which is 7.53. But if everybody's went up by the same amount, 1.18, the standard deviation shouldn't change, so it should still be 0.59. So you'd have 7.53 plus 0.59 would be 8.12, and then plus 0.59, 8.71, plus 0.59, 9.3. And then below would be 7.53 minus 0.59 minus 0.59 and minus 0.59 be 5.76. And again, 34%, 34%, 13.5%, 2.35%, 0.15%, 13.5% here, 2.35 here, and 0.15 here. Okay, question number 6. The longevity of a cell phone is normally distributed with a mean life of 2.5 years and a standard deviation of 0.5 years. For how long should the warranty be if the company wants to repair no more than 2.5% of the phones sold? So if we look at our standard normal distribution labeling, this would be a mean of 2.5 with a standard deviation of 0.5. So this would be 3, this would be 3.5, this would be 4, this would be 2, because take off 0.5, take off another 0.5 would be 1.1, and take off another 0.5 would be 1. And we know that this would be 34%, 34%, 13.5, 2.35, and 0.15. 13.5, 2.35, and 0.15. Okay, so if they want to repair no more than 2.5% of the phones sold, then they'd have to be looking at basically only keeping their warranty for this amount of time, because 0.15 and 2.35 adds up to 2.5%. And if the warranty is any longer than 1.5 years, you're getting into a higher percentage of the data. So therefore, the warranty should be for up to 1.5 years. Anything longer than that, they're going to end up replacing more of the data, because only 2.5% of their phones will last less than 1.5 years. So there's some questions there now at the bottom in your textbook that you can try that are related to questions that we've done in this section.